The dividend discount model says that the intrinsic value of a share of stock, that is, what we think the stock should be worth, is the present value of all future dividends. In equation format, we see that here. V at time 0 is the intrinsic value today, and then these terms on the right side represent the series of future dividends at times 1, 2, 3, etc. And then the denominators reflect the discounting of each of those to the present. Now we've also learned that this equation can be equivalently written as the present value of all expected future dividends up to some future date h plus the present value of the price at that same future date h. And so again, these formulas are equivalent to one another. That's very nice for us because with that recognition, we can either, to value a stock, estimate all future dividends and discount them appropriately, or simply pick some reasonable future date h and estimate all dividends up to date h and estimate a price at date h and find the present value of that series, and so essentially use this formula. Now let's talk about some special cases in which the dividend series follows a specific structure. And these are useful cases because they allow us to take this very general dividend discount model formula and simplify it to something much more usable. There's three cases that we're going to look at now. The first is the constant dividend case. There we'll see the stock is valued as a perpetuity. The second is a case where dividends grow at a constant rate, and this will give us what we call the Gordon growth model. And the third is a variation of the second, and here we're just going to have two growth rates. So we're going to have an initial period of potentially high growth and then a terminal period of stable growth. And we typically call this situation a two-stage or multi-stage growth model. Case 1, dividends are constant. This typically means that the firm has no growth opportunities, and so it's simply going to pay all of its earnings as dividends and do so forever. In other words, all the dividends are the same. And so looking at the equation, these numerator terms become much more simple. So instead of individual values for each one of these dividends, we would just say dividend at time 1 is equal to dividend at time 2 is equal to dividend at time 3 equals so on, and all of that is equal to the firm's EPS. Now moving to a timeline. We'll see a series of constant EPS amounts here, and we should know by now that that timeline is simply a perpetuity, and the value of perpetuity is the perpetuity amount divided by the discount rate, and so V0 in this case becomes EPS divided by K. Here's an example. Firm pays out all of its earnings as a dividend, so we know that's going to be a perpetuity. We have a discount rate. We should be able to solve for the intrinsic value. So the timeline looks like this. The value is EPS divided by K, which is 5 divided by 15%, or $33.33. Case 2, dividends grow at a constant rate. And in order for this to happen, you can imagine a firm that has some growth opportunities, and so it's going to take its earnings and split that into a dividend component and a reinvestment component. And because of this reinvestment in new projects, future earnings and dividends are going to be larger than current dividends. Here we've got a really simple structure where the growth is going to be constant forever. And so what does that mean for our valuation formula? Well, once again, we'll start with the basic dividend discount model formula, and then we're just going to deal with special structure for these dividends. And so because we have this constant growth rate G, we know that dividend at time 2 will equal the first dividend times 1 plus G. And then if we move forward, we also know that the dividend at time 3 is equal to the second dividend times 1 plus G. But of course, since we've already identified what the second dividend is, we could also write D3 as D1 times 1 plus G squared. And then we can continue writing all of these dividends as such. Now go into a timeline. Just write the first few. We have D1 times 1 plus G for D2, D1 times 1 plus G squared for D3, and then this is going to continue on forever. And so the upshot of this is if we know D1, we can use the growth rate to determine all other dividends going forward. We call this structure a growing perpetuity. And it has a very simple formula as well. So here we have V at time 0 is equal to D1 divided by K minus G. Now we may, instead of knowing D1, we may know the dividend at time 0. We can write it in terms of the dividend at time 0 as well, because we know that this constant growth rate is going to apply between time 0 and time 1. And so we could also write this as D0 times 1 plus G divided by K minus G. So once again, here is your formula for the growing perpetuity. We have a special name for this formula. This is called the Gordon growth model. So anytime you hear Gordon growth model, just think, hey, this is a constant growth dividend case. An example for case 2, we see a firm with an earnings of 5. We recognize this firm is keeping some of its earnings and reinvesting in new projects and then paying the remainder out as a dividend. So we get a $3 dividend per share. We do have this growth rate again of 8% into perpetuity. One quick thing to note here is this $3 is the dividend it just paid, so we think of that as D0. And so we have to, for our formula, we have to say D1 is equal to D0 times 1 plus G. Now taking that to the Gordon model formula, we have the intrinsic value is equal to this term, inserting the appropriate numbers. We have 3 times 1 plus 8% in the numerator, and we have 15% minus 8% in the denominator. Intrinsic value for this stock is $46.29. Case 3, dividends grow at 2 different rates. So as we move closer to reality, we want a model that is flexible enough to allow something other than just the simple constant growth that we see in the Gordon formula. And so here we take a step in that direction by allowing for 2 distinct growth rates. The first, that we'll call G1, is a short-term growth rate, and that's only going to apply for the first, call it T years. And then we'll have a long-run stable growth rate, we'll call that G2, and that's going to apply thereafter. And so the way to think about this case is at some point down the road, specifically T years down the road, this firm will become a constant growth firm. And so we can account for that by estimating what we think that terminal price, or PT, will be. And then the other thing we need to account for is this intermediate period where dividends are growing at a higher rate. And so those are the dividends growing at the rate G1. And so the steps that we need to calculate an intrinsic value here are, first, we want to estimate the first T dividends. Then we're going to estimate the price at time T, or PT. And so recall, for step 1, we're going to need the growth rate G1 because it's going to govern the dividend process. And then to estimate P2, we're going to need this long-term growth rate G2. And then once we do steps 1 and 2, we can use our outputs to create a timeline of a series of cash flows. Then we simply need to discount all cash flows to the present. Okay, so let's get a clean slate here and walk through the steps. So first, again, we need to estimate the first T dividends. And for those dividends, we need the growth rate G1. And so we know that D1 is equal to D0 times 1 plus G1. D2 is equal to D0 times 1 plus G1 squared. We could do that all the way through dt, where dt is equal to d0 times 1 plus g1 raised to the t power. So let's go ahead and start building our timeline now. Go to time t plus 1. And so if we've done these calculations, we'll have d1, d2, all the way to dt calculated. Next, we need to estimate the price at time t, or pt, and for that, we're going to need the growth rate G2 and some other stuff. And so recall once again that at time t, growth is going to be constant going forward, and so the Gordon model will apply. And so we can say PT is equal to the next dividend, so that would be dt plus 1 scaled by k minus the growth rate, and the growth rate here is G2. We also recognize dt plus 1 is dt grown 1 year at this new constant growth rate G2. And so we could write the numerator this way as well. Either way, we get to an estimate of PT. And so then we can take that and put it on the timeline also. So that's going to show up right here. Now, one quick question. What happens to the dividend at time t plus 1? Do we need to show dt plus 1? No, we don't, because that's accounted for in the calculation of PT. And through this growth that happens going forward, every dividend after time t is accounted for in the number PT. And so dt plus 1 and all future dividends do not show up explicitly on the timeline because we have the term PT. Now the final step is to just discount all of these cash flows to the present. So we can do that by discounting them one at a time. So we'll have a series of terms that look like this, and I'm actually going to make this a little bit simpler, even though these occur both at time t, I'm going to separate them. So we'll say dt, should be a 2 there, say dt divided by 1 plus k to the t, and then plus pt also divided by 1 plus k to the t. And so we'll think of this set of terms as the present value of the dividends through t, and this final term as the present value of a terminal price PT. Here's how your textbook writes this last big formula. It says the value is equal to the sum of the present values from 1 to t of these first dividends so this is again just the summation notation for the dividends from time 1 all the way to time t, plus this term dt times 1 plus g2 divided by k minus g2 divided by 1 plus k raised to the t power. So what the heck is this last term? Well, if you look at it really closely, you'll see that this is something we've already calculated. So go back here when we calculated PT. See, there's PT showing up. And then if you go up here, we took PT and divided by 1 plus k to the t. There's the 1 plus k to the t. And so this equation and this equation are the same. Finally, let's work an example. So we got, again, a firm with an EPS of $5, and it just paid $2 of that as a dividend and then reinvested the rest in profitable projects going forward. And so we see that we've got a really high growth in dividends of 16% per year. So that's going to be our G1. And that's going to happen for T equals 3 years. And then after that, we've got stable growth of 5%. So that is our G2. And so to solve this problem, we need to estimate D1, D2, and D3 using the G1 of 16%. And then after that, we will estimate P3, which is the price, and that's going to be the price of a stable dividend growth stock, and the growth rate there will be the G2 of 5%. And so D1 is D0 times 1 plus the high growth rate, which is $2.32. D2 is 2 times 1.16 squared, or 269. And D3 is 2 times 1.16 to the third power, or $3.12. Let's go ahead and put those on our timeline. We get the 232 here, 269, and $3.12. Now P3 is equal to the next dividend. The next dividend is D3 times 1 plus the growth rate G2. In the denominator we have K minus G2 because it's a stable growth situation thereafter. Inserting the numbers, we have in the numerator 312 times 1 plus 5%. In the denominator we have 12% minus 5%. This gives us 46.83. Put the 46.83 on the timeline as well. We'll go ahead and write the plus there, so we'll remember that this is also a time 3 cash flow. Okay, so we got our timeline ready. Last step is just to discount each of these to the present and sum them up. So the discount rate is 12%. So we'll see some 1 plus 12% raised to an exponent values in the denominator. We'll sum all of these up and we get the intrinsic value of the stock. And that number is $39.77.